Hello everybody and welcome. So we're going to get started on our artistic approach to maths by looking at something pretty simple but often overlooked. Now we all know sort of basic mathematics, basic algebra when it comes to sort of adding, subtracting numbers, multiplying, dividing, right? So there's some basic things that we at least probably all retain when leaving high school or whenever the last time it is that you did some maths at school. But one of the things that's often overlooked is actually the relationship between these pairings. So addition and subtraction, multiplication, division, they all have a sort of a ratio or a relationship between one another and a way to work going from one to the other. And this comes up a lot in 3D because we often want to feed in a bunch of parameters, maybe a ramp, or some attribute that is being defined by something else in a simulation. And we want to drive something based on that, but then something else kind of in the opposite direction as well, right? So we need to sometimes convert from addition to subtraction. Now, when it comes to addition, we all know, something like 2 plus 4, right, is equal to 6. But 4 plus 2 is also equal to 6. So you see there, the order doesn't matter when it comes to addition. However, when it comes to subtraction, the order does matter. 2 minus 4 is negative 2, but 4 minus 2 is 2, right? So that's a very big difference. That's a difference of an entire sign, right? So the order there matters. But we can essentially express subtraction in the form of addition using a function called negate, right? So instead of thinking of 2 minus 4, we are essentially going 2 plus negative 4, okay? So this negative sign, this minus sign, is actually attached to the 4. And so if we negate the 4, then we essentially have addition. And in this way, the order doesn't matter again. So negative 4 plus 2 or 2 plus negative 4 is going to give us the same result. And the function that we're using to do this is called negating, okay? So it's just simply multiplying by negative 1, or in a more visual way, it's essentially just swapping the sign. So if it was positive, it becomes negative. If it was negative, it becomes positive. So for example, 2 minus negative 4, okay? So if our 4 was actually negative in the first place, well, we can still do the same thing. It's just that we negate the negative 4, so it would become 2 plus positive 4, okay? So in other words, we're back to the same addition sum at the top. And negating is actually a function that we find in VOPs. And in VEX, it isn't a function on its own, but you can simply just multiply by negative 1. So you'll see here, 2 multiplied by negative 1 gives us negative 2, and negative 2 multiplied by negative 1 gives us 2, right? Very simple. We're essentially just altering the sign at the front, okay? Very simple technique, but often overlooked because when it comes to the order of operations here, we don't want to be bound by something that it has to be this minus that. It gets very confusing. Whereas in a lot of the ways, like when we're working with VOPs, and especially when we get to working with vector maths, as you'll see later on, the same principles apply. When we want to subtract one vector from another, but often we find it very difficult to control the order that we have those two vectors. And so instead we want to add them together, but negate the one that we want to be used as essentially subtraction. Okay, so we're going to see more examples of how this works for us later on, but it's important to bring this up because I find that a lot of students don't know this function, or at least that it's called negating. Okay, now negating is distinctly different from inverting. Okay, so that's the next thing we're going to be talking about. So multiplication and division sort of have a very similar relationship to addition and subtraction. With multiplication, the order doesn't matter. 2 times 4, 4 times 2 is still going to give us 8. However, when we get to division, of course, the order matters again, because it essentially matters which number is on top, right? 2 divided by 4 and 4 divided by 2 are very different results. So how do we represent this division, but in terms of multiplication? Well, we just use the invert function. And the invert function is ultimately just 1 divided by x. So in other words, 1 divided by the number that we're trying to divide by. So 2 divided by 4 is the same as 2 multiplied by 0.125, right? Now, some of these numbers actually stand out for us pretty easily. For example, we all know that dividing something by 2 or multiplying it by 0.5 is the same thing. Okay, I think most people at least intuitively understand that. But when these numbers become a little bit more complicated, maybe we're dividing by 1.682, well then what is the inverse amount of that? So it is good to know that in order to invert it, what we need to do is 1 divided by x. Okay, so you'll see this come up a lot more often, but I'm going to show you a graph here that is going to also help understand what's actually happening with these numbers and how they relate to one another. Now, when you use VOPs, you'll find that there are nodes for all of these 3 that we're going to be talking about. There is a negate node, and in fact, the little icon on the node has an x times -1. So it actually reminds you what it does just by the icon on the node. And the invert node also has 1 divided by x. Okay, so it's just a way to help you remember if you are using VOPs. So when it comes to inverting a number, right? So essentially these 2 numbers have a relationship to one another. 2 is the inverse of 0.5, but it also works the other way around. 0.5 is the inverse of 2, because if you go 1 over 2, it's 0.5. And if you go 1 over 0.5, then the result is going to give you 2. So these 2 are essentially just the inverse of one another. And if we sort of plot these on a graph, okay, so we have a graph here, we've got 0, 1, and okay, I haven't put in the numbers here because I didn't want to clutter the screen, but it's 2, 3, 4, 5, so up to 10. Okay, so we're looking at a 10 by 10 grid here, right? And I put in 2 here because this is the one that we often sort of intuitively understand, that 2 and 0.5 are inverse numbers of one another. Now, you'll see what happens when we plot this on a graph, and actually we can now increase or decrease this number and see all these inverse numbers of one another. So for example, 2.38 and 0.42 are inverse of one another. Okay. Now, what happens at exactly 1 is that 1 is the inverse of 1, because 1 divided by 1 is 1, and vice versa. And so you can see this kind of strange relationship where sort of mirrored around the number 1, okay, or this 0 to 1 range versus 1 upwards, sort of forms like an inverse relationship. Okay, you can even see here, look at how this curve goes down, and then from this point it curves up in the exact same way, right? And it all mirrors around the 1 mark, so 1 and 1 on x and y. Okay, so I just find this quite interesting to sort of visually see how these numbers relate. As we increase this, then you'll see that this number decreases, okay? But it decreases in a sort of slower and slower. So from 1 to 2, this number is reducing quite a lot. But over time, as we increase this, then our other number, our inverse number, kind of slows down and reduces by a lot less, because this graph is actually flattening out, right? So at 10, we have 0.1, okay? And that's, again, is another one that we often understand. If you want to multiply something by 10, well then divide by 10, well, you can multiply by 0.1, okay? And then, of course, it works the other way around as well. If we go below and we say 0.1, then the value is going to be 10. Okay, so these are just 2 sort of in relation to one another. Right. So let's move on to power and root. Now, ultimately, power and root are just sort of one one step further, just one generation further than multiplication and division, but they are based on the same principles. So we always know about the sort of, square and cube. I'm sure you remember that part of maths at least. So 2 to the power of 3 is 8, because it's 2 times itself and then times itself again. So, times 2 again. So it's 2 times 2 is 4, and then 4 times 2 is 8, right? So very simple. That's what power is. And then you have square root or cubed root or fourth root, or essentially it's the inverse function. Okay, so you can go from 8 to 2 by cube rooting it, right? Now, in Houdini, we actually find that there is a power function, both in VOPs and VEX, right? And even, I think, in H script, you can raise something to the power of, so it's an exponential function, right? But the root function only has a square root, right? So there's a sort of a convenient square root node in VOPs, but there is not just a sort of like a root node that lets us say, cube root, or to the 1.86 root. We can't feed it a sort of float value like that. What it does is it expects us to understand that raising something to the power of, if we instead want to find the root of it, so the cube root instead of 2 cubed, you use the inverse function. So you invert the number that you're looking for, right? So the cube root of 8 is the same as saying 8 to the power of 0.33 recurring. So 333, however far you want to go with the floats, right? So how we got to 0.33 is 1 divided by x, so the number that we're looking for. So for example, maybe an easier number to understand is squared. So 2 squared is 4. But then the square root of 4, right? We would just say 4 to the power of, and then instead of 2, it's 1 divided by 2, okay, which is 0.5. So 4 to the power of 0.5 is going to give us 2. Okay, so this number you'll see, and in fact we can see it in this graph, when we go, when the number is above 1, then the other number is between 1 and 0, okay, and it always crosses at 1. So the 1 is always above 1 and the other is between 0 and 1, not into the negative. It's really important to note that no matter how low we go, this will never cross into the negative, okay? You can invert negative numbers, but then the sign just remains the same. If it's negative, it's negative. If it was positive, it stays positive. What happens here is there's a ratio between sort of 0 to 1 versus 1 up to infinity. Okay, and the inverse number is always in the opposite one of those quarters, right? So like all those sort of segments. So if we take this higher and higher, this number just goes lower and lower, but just closer to 0, and yet it will never fully touch 0, the same way that this number can never fully reach infinity. Right, so that is, sorry, just got a little lost there. That is what's happening over here, where we're inverting this number, and so it essentially is saying this is the root of, so it's the cube root of 8 is 2, by going 1 divided by 3, right? Now, if we represent power on a graph, what we get is something quite interesting and also quite familiar, because a lot of the time you'll find that when we're trying to create any kind of ramps in Houdini, maybe we want a sort of acceleration ramp or even just our color or whatever, we often draw the sort of kind of like an arc like this, okay, which gives us some nice results, right? It's essentially, this is easing out and easing in, okay? So the white graph would be easing out, blue would be easing in, right? And these two are essentially just the power of, right? So raised to the power of something. So for example, this gray line in the middle here, this is linear. So 0.1 is 0.1, 0.2 is 0.2, and so on, okay? So it just, that is our linear number line. But the white graph over here is showing raised to the power of whatever I have input over here. Okay, so right now what we're looking at is a square graph. So between the numbers 0 and 1, what happens is 0 stays 0, 1 stays 1, but all the numbers in between seem to dip down towards 0. Okay, so for example, let's take 0.5. If it's raised to the power of 2, what that means is you multiply it by itself. So what is 0.5 times 0.5? In other words, half of 0.5. Well, it's 0.25. So you'll find that at this point, between 0.2 and 0.3, if we traced a line, we'd find this lines up with 0.5. Okay? So it essentially 0.5 halves itself. 0.25, so a quarter, quarters itself. So actually, if you look at this line of where it should be versus where it now is on the white graph, that is 1/4 of the way down. Okay, so like if we sort of took that amount on top of itself, we'd be halfway, and then another quarter, and then another quarter, and then we're back at 0.25. Okay, so these numbers are essentially reducing themselves. So the smaller they are, then the smaller it gets reduced. But then as soon as we reach 1, it doesn't matter what our power is, 1 times itself, however many times, is always going to be 1. So it meets at 0, it meets at 1, but it dips in the center. And then you'll see that the blue line is our inverse graph. Okay, so remember we said that the inverse of 0.5 is 2, okay? So instead of now going, so at 0.5, we multiply by 0.5. Instead, it's raised to the power of 2, so it's 1 divided by 2, so it's raised to 0.5. So when it's raised, so in other words, 0.5 to the power of 0.5 is 0.75. So the number increases. Okay, so you'll see that the smaller the number is, the more it kind of increases above what it should be. And then as it reaches 1 and 0, they meet again. Okay, and if we extend this graph, then you'll see what happens beyond 0 and 1 is quite interesting. It's kind of the opposite. What started as a graph that became essentially less than the original number, at 1 it crosses and now becomes more than the original number. So don't forget that gray is the original. So at this point over here, we're looking at maybe like a value of 10, okay? Or actually, no, sorry, hang on. We've doubled it, so this is 2, okay? So we're looking at a value of 2 here. But 2 to the power of 2 would then be 4, so it would be way up here, right? And the blue graph does the opposite. It slowly, essentially flattens out. So if we kept extending this and going, you'd see that it'll eventually flatten out. Well, not perfectly, but almost. It tends towards a sort of a slope of 0. The gray is a perfect linear slope, and then the white one just keeps climbing and climbing. Okay, and this is how we work with exponential numbers, right? So when we draw those curves, we're essentially trying to mimic this, but we can do it through maths. Just without having to even draw those ramps, we can just take a number and put it to the power of something, 2 or maybe 3. In fact, when we fix our colors, our gamma, we multiply to 2.2. Okay, so gamma of 2.2 is essentially applying this curve to your colors. And then when you want to return to linear color space, you simply multiply by the inverse of 2.2. So it's 1 divided by 2.2, and that's what you raise to the power of in order to get from the gamma corrected color space to linear. Okay, so we use this all the time, but it's important to understand how and why. Now, I always tell people one of the most important things to understand, especially when it comes to effects and animation, like motion, or anything like maybe where you're scattering points. So you've got hair on a character, or maybe distributing grass on like a ground plane. Nothing in nature is ever linear. It's just something that nature does not do, is have linear numbers. If something moves, it doesn't just suddenly move at top speed, it accelerates. Okay, even due to gravity, even something as consistent as gravity is an acceleration, not a linear speed. If you've got, character maybe has really hairy arms, but toward the sort of hands and knuckles the hair fades off, it will never fade off just linearly. It will always fade in a slightly exponential way. It's not necessarily perfectly squared maybe or cubed, but it's at the very least not linear. And so being able to know and understand what the curve of power looks like, so for example, to the power of 2 means that our numbers over here are going to be less and then more, or the inverse, okay, so 0.5 means that they swap, so now it would be more and then less. If we understand that ratio, we can, without having to draw curves all the time, we can get much better results in our simulations by, instead of feeding in linear numbers, we feed in exponential numbers. Okay, so extremely important technique, very useful for practical reasons. Now, the final one we're going to be looking at in terms of these three ways of finding the opposite ratio or sort of relationship is complement. Now, complement's a very simple one, but it's actually one that a lot of people don't know the name of. So if I say to most people, what is the complement, they don't even understand the question. And yet it's probably one of the simplest to understand. It's simply just 1 minus x. And the easiest way to see that is when we look at percentages. So percentage, we all know, so something like 70%. But 70% really is mathematically represented as 0.7. Okay? Because if you multiply something by 0.7, what you're getting is 70% of the original. So in a sort of 0 to 1 number range, that is our 0 to 100%. Now, of course, you can get more than 100%, and that's why this number range, you can go above 1. But if we're sort of just talking about portions of a whole, then we are fixed between 0 and 1. And so 0.7 we know to be 70%. But what about the rest? A lot of the times we have the number 0.7, but what we actually want is the other portion, okay, the opposite portion that's remaining. And sure, 70%, that's easy. We know that the other percent is 30%. But when it becomes more complicated numbers, what is the complement of 0.5836? Then it's like, how do I convert that just straight away in my head? Well, the sum is really as simple as just 1 minus 1 minus x. So 1 minus the number of the ratio that you already have will tell you what remains. And this can be extremely useful because let's have a look at this graph over here and I'll show you why. So once again, I'm just going to remind you that in VOPs, you'll see these numbers actually, so 1 minus x and 1 divided by x on the actual nodes of these, and it will be called complement. And so that's just a nice way of sort of remembering it. If you're not sure what they do in VOPs, just zoom in a bit and you can see on the icon it actually shows you. Now, when we come to a curve like this, a lot of the times we'll have a ramp. And maybe, for example, let's just say in a simulation, I've got a ramp that is driving the release of some particles. Okay, so it starts at 0, but slowly over time, I want to release more particles, but maybe there's a big burst, so it accelerates and releases a lot more particles and kind of tapers out at that amount. And then toward the end, suddenly starts releasing twice as much. Okay, so this is the curve that I draw. But I also want maybe the scale of these particles to also be driven by the same ratio. But the problem is what I want is actually when I have very few particles being released, I want very large particles. So their scale must be large when there are few of them. And the more that are released, the smaller their scale becomes. Now, we could go and put two separate ramps, one sort of linked to the amount of particles, the other one linked to the scale of those particles, so the p scale, right? But now I then have to manually maintain the ratio between these two ramps when I want to maybe change one. So I run my simulation and I say, oh no, actually I want to shift that keyframe, so I'm just going to move maybe the center point of this graph a little bit to the left. Well, now I have to do the exact same thing on the other graph so that the ratio remains exactly the same, and I have to get the slope of every curve, like every point on the curve, correct, and that is a pain. So instead, what we can do is just mathematically convert from the one portion of the ramp to the other. Okay, so here on my ramp, when I am at, let's say, 0.41, okay, so I'm releasing, 40% of the 41% of the number of particles that I will eventually be releasing, then their size should be 0.59 of the size. The smaller this number gets, sorry, dragging the wrong thing. The smaller this gets, so the fewer particles are released, then the larger this number gets. And we can simply just, because it's a 0 to 1 ratio, we can complement from one number to the other, okay? So we're essentially just grabbing the other portion. And now we can apply this side to our scale and this side to the number of particles. Then I can have just one curve, but that curve is being fed in through the complement function into the scale and fed in raw into the number of particles released, so the density of the released particles. Okay, and then as it increases, then the scale decreases. All right, so very useful to be able to convert in the 0 to 1 range from one to the other. Very useful to be able to convert from one exponential function to the inverse amount, either so that we can get back to linear, or so that we can have it increase at first and then decrease, or the other way around. Extremely useful to be able to work with multiplication and division in such a ratio where we don't want to have to actually divide. The order won't matter anymore, and we can simply multiply by that amount. And we also know how much to multiply by, so the inverse amount, to get back to 1. And then the same with addition and subtraction. We can remove the whole order, kind of situation by just simply negating a number. And all of this is going to be incredibly useful when we get to vector mathematics. Okay, so I know these are basic mathematical principles that you should remember, but seeing them visually and how they have a relationship to one another, I hope will help you understand how to just work better with Houdini and the numbers that we feed it. Okay, all right, so moving on, we're now going to be talking about a few functions that I've found to be incredibly useful when talking about ramps, numbers that were input, or even, driving simulations with these. So extremely practically useful functions, but that a lot of people seem to overlook. So I wanted to highlight these to you so that you understand what they do and how to work with them. Now, the absolute function essentially just what it really does is it measures the length of that number, the distance of that number to 0. But what it really does for us is it drops the sign. So when we say the absolute of 3, it'll give us 3. But the absolute of -5 gives us 5. So essentially it just drops the negative sign, making it only positive. So this can be incredibly useful when we want to do maybe noise functions, but we don't want anything to dip below 0. I've also just very recently used it when making clouds, because I want to scatter some random particles, but if I'm building a cloud at the origin, I can then make sure that any random particles that form that cloud that go below the sort of horizon go up instead of down, and so you end up with a flat bottom on the cloud, which is a lot of what the sort of stylized cartoony clouds look like. So very useful function, absolute. Now if I take this on, you'll see here I've got a curve showing just, some values that go positive, then negative, right? And then back into positive. But if we switch on the absolute, if we just fed that exact same graph, the exact same numbers in to the absolute function, then this is what we get. So in the beginning, it's exactly the same, does not alter the numbers at all if they are positive. But as soon as it crosses the boundary into negative, then it just goes positive, right? And this is exactly what our alligator noise is actually doing. So if you see on the turbulent noise function in VOPS, you'll see the alligator noise. Alligator noise, I mean, I think you can even see why it's called that. It's like the sort of ridges on the alligator's back, or like the scales. It's only positive values because they've got these sharp peaks over here, right? Because we're not simply taking just a graph and then having there be no negative values by taking all these numbers and rising them up. So just adding numbers to them until this is above 0, because then that would still look like this nice smooth curve. It would just be a lot higher up here, so not dipping into 0. But if we absolute it, what happens is we get these nice sharp peaks. I mean, I say nice, look, sometimes that's not what you want, but if you ever do want these sort of sharp changes in direction, sharp sort of fall offs, and then nice loose sort of smooth peaks at the top, then this is something you can do with your noise. You can use an alligator noise function, or you can run your own noise, sparse convolution or Perlin, whatever you want, and then you just take the noise function and put it through an absolute, and then it will return only positive values. For example, to go back to the cloud example that I used just now, if instead of basically absoluting, if we clamped all values below negative, so below 0, to be equal to 0, so clamped it to 0, then we'd end up with a flat bottom, sure, but we would lose this kind of definition. So it would go up, and then here it would be flat, and then it would rise. Sometimes that is what you want, okay? So maybe for calculating collisions or whatever, you want things not to actually bounce back, but actually just flatten against the edge, right? So sometimes it is right to clamp values if that's what the result you're after. But if we absolute, then we have it, and it takes all of this distance that it would be going into the negative and instead sort of mirrors it, just flips it up into the positive. Okay, and then maintains all other positive movement. So that can be an incredibly useful function for you. Now, I want to bring up the opposite, well, there's sort of a slightly confused version. A lot of people kind of get negate and absolute confused because it will sometimes give you the same result. -5 negated or -5 absoluted give you 5. Right? So there are some times where it does the exact same thing. This area, for example, you'll see here, the red overlaps in the middle where our green overlapped. But in all the other areas, it's the opposite, right? It negates everything. So positives become negatives, negatives become positive. It literally just mirrors the whole graph, whereas absolute only mirrors the negative values. Okay? And so this might be what you want. Also, sometimes you actually want to use a combination of absolute and negate, although the order does matter, right? Because maybe what you want to do is get those nice sharp peaks, but you want them to be going underneath, okay? So then what you would do is you could absolute it, so then you get this green graph, and then if you negated the green graph, then you'd end up with the red where it would go to here, and then it would follow this along the white, and then here along the red. So then you'd end up with an upside down version of what we had on the green. Okay, so a combination of these can give you different results, but just do not confuse negate with absolute. Absolute makes everything positive. Negate will swap it depending on what it already was. Okay, so it just reverses the sign. Okay, so very useful function there. Now, the next one we're going to look at is called modulo. Okay, so this is a sort of the modulus of a number, right? So If we take 5 modulus to 2, it gives us 1. And 8 modulus to 4 gives us 0. Now what is actually happening here? Right, so let's examine what is actually happening. And I just want to point out that the modulus function is the percentage sign. And you can actually type it like this inside of your parameters in Houdini or in Vex. You can literally put 5 and then %2, and it will return the value 1. Okay, so this is universally used as the modulus sign. Now what's happening with modulus is we're dividing by the number, right? The second number. But what it returns is the remainder. Okay, so instead of doing the perfect division, so 7 divided by 2 gives us 3.5, right? But instead of doing that, 3.5, if we divide it only into integer numbers, and then we have a remainder. So 7 divided by 2 is 3 with a remainder of 1. 1 that cannot be divided because 1 divided by 2 would give us a fraction. Okay. Then the modulus of 7, so 7 modulus to 2 is 1. Okay, so it's basically just saying divide this number by this number and then give me the remainder. Now, why is that useful to us? Well, let's have a look at a graph that shows exactly what that's doing. So if we take x modulus to 3, right? So we have a number graph here. So maybe these are frame numbers. So x is actually our frame number. And then as our timeline moves forward, x is changing. So it starts as 1, then it goes to 2, then 3, and so on. If we modulus to 3, then what happens is we end up with this sort of zigzag. In other words, it increases linearly, so it matches our linear growth, but then suddenly it resets back to 0 and starts again. And you'll see that this white line and all of these, so this section of the blue is parallel. Okay, so this does follow linear again, but it's just that it started again from 0, and then it loops back and then starts again, and then loops back and starts again. So we end up with essentially a looping number. Okay, and so for example here, 1 modulus to 3. Now remember, if we go 1 divided by 3, it'll be 0 with a remainder of 1, because we can't divide 1 into 3 perfectly. 2 divided by 3, again, same thing. It'll be 0 with a remainder of 2. But then 3 divided by 3 gives us 0, right? It gives us 1, but with a remainder of 0, right? So that's why it loops. When you have the perfect, so 3 into 3, it gives us, so modulus of 3 to 3 gives us 0, because the remainder is 0. In other words, it is a perfect division. Okay. 4 modulus to 3 gives us 1, because again, 4 divided by 3 will give us 1 with a remainder of 1, right? So it gives us the same number as here, because it doesn't care about the amount that gets perfectly divided, only about what's left over. 5 modulus to 3 gives us 2, and then again, when we hit 6, because 6 divides perfectly into 3, then the remainder will be 0. And so this is why it loops back every time to 0. So now we end up with a looping number system of 1, 2, and then 0, 1, 2, 0, 1, 2, 0, 1, 2, and it'll keep going infinitely. And so we can choose how many sort of numbers we go before it loops. If we do modulus to 3, that means we're going to have 3 integer numbers before it loops. Now it does always start at 0, because when you have perfect division, the remainder is 0. But let's say you wanted a loop that goes maybe 5, 6, 7, 5, 6, 7, 5, 6, 7, okay? You would still do modulus to 3, but then you would just do like frame number, so $F modulus to 3, and then you would just plus 5. So then it would be, 1 plus 5 would be 6, and then 2 plus 5 is 7, and then it would go back to 5. So it would be 6, 7, 5, 6, 7, 5, 6, 7, and that's how it would go forward, right? And of course, if we started our frame number at 0, then we'd first get our 0 over here, because 0 divided by 3 will have a remainder of 0 as well. Okay. So it's just important to just point out here in my number graph, by the way, that it goes 0, 1, 2, and then it looks like it reaches 3 here, but it actually doesn't. It's just the way that this graph is going, is that it's increasing linearly until it hits like the second it actually hits 3, it becomes 0. So 3 is at 0. It's just that 2.999 is still on the same linear path. And then the second it actually crosses into 3, then it jumps down to 0. So even though this looks like it goes up to 3, it really goes up to just below 3. Right? This is if we feed it float numbers, but obviously if we fed it integers, then it would look a little bit more like a step, and it would go 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay. So modulus, very often overlooked, but extremely useful, because a lot of the time we want looping numbers. Maybe we want some kind of repeated animation, or maybe to release some particles. So we release, sort of increasing number of particles, and then we reset, and then increasing number, or, maybe rising of like a glow attribute. So it's like a siren kind of spinning around, or sort of pulsing, glowing, and then jumping back to 0. Okay. Now this will not be a smooth, it won't sort of go up and then smoothly down. It's going to increase, 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 and then jump back and reset, which sometimes is exactly what we want. So modulus is the way to achieve that. All right. And then finally, what we're going to look at is rounding. Okay. Now, rounding sounds quite simple, and it is, but there are some extremely useful practical applications for what we can do with rounding. Okay. So let's first just discuss the types of rounding that we have, because a lot of the time these are kind of a little misunderstood. I think the most common that we all understand is the normal sort of rounding something to an integer, which basically is that when it's 0.5 or above, it gets rounded up to the nearest integer. So 4.8 becomes 5. Even 4.5 becomes 5. Okay. So at the halfway point, it always goes up. But at 4.499, it would go down to 4. Okay, and everything below that would go to 4 until it crosses then to 3.9, which would then still be 4. And then 3.4 would then go down to 3. Right? And so what we end up is with the stepping, and the stepping kind of happens at the 0.5 mark. So you'll see all of these numbers, the gray is just linear, and then the purple is the rounded numbers. So these are getting, no matter where they are, they become 0. Here it becomes 0 until now suddenly it crosses 0.5, and then it goes, okay, well now I'm 1. Okay, and so then that stays 1 until it crosses the 1.5 mark, where it then becomes 2. And then it stays, and then it increases and increases. Okay, so it steps exactly the same as these other rounding functions will step, but it just depends on where it ends up on either side of our linear line. Okay, with normal rounding, it kind of zigzags on alternate sides of our linear line. Okay, and sometimes this stepping is exactly what we want. Sometimes we don't want a smooth amount, but we actually want things to kind of jolt or jump forward, right? If we want to do some kind of shaking thing or something sort of linearly increasing, then we can round it this way. Now, and also it's just important to note that if you automatically have something rounded from so you're feeding it a float value, but it's being fed into an integer, it will round this way. And maybe that's what you want, but if you don't want it, then it's important to know the other ways of rounding it so that you can round it on your own to get the result that you're looking for, and then just feed that number into the integer. Okay, so there are two types here, ceiling and floor, and ultimately they just are round up and round down. Okay, so with ceiling, we're basically saying, I mean, obviously the ceiling is above you, it's, round up. It's just very easy to kind of understand. You can imagine a balloon in a room will be rounded up to the ceiling. Okay, so it will just float up and hit the ceiling, and then only when it maybe goes, if there's a gap in the ceiling and it goes up to the second floor, then yes, then it will rise up. Okay, so ceiling just means 4.2 becomes 5. 4.8 also becomes 5. They round up. So same stepping, but it just immediately goes up to 1 and then stays at 1. And then as soon as we cross the 1.1 threshold, then it goes right up to 2 and just stays there. Okay. And then floor just gives us the opposite. Floor just rounds down. So 4.2 will be 4, 4.8 will still be 4, and it only becomes 5 when it actually crosses the 5. So 5, 5.1, 5.2, those will all just be 5. Okay. And so exactly the same thing here, just round down, and then only when we cross the 1 does it then go up to 1. Okay. So let's have a look at what we can now do with that rounding that can be something quite useful for us, right? So what if we want to have numbers? Now, I've shown you here with modulus how we can then have things sort of increasing and then resetting, okay? Which is often something that we want in some kind of, some of our settings. But sometimes we also want stepping. We literally want what we're looking at here, this kind of stepping, but maybe not, this is stepping in individual units. This is going up by 1 every time. But what if we literally want to have, maybe it stays 1 for 5 frames, and then it increases to 2 for 5 frames, and then it holds on 3 for 5 frames. For example, maybe we want to release some particles, but from one of our objects. So we have 3 objects numbered 0, 1, and 2. And then we say, okay, well, I want to release from object 0 for a few frames, and then switch to releasing from object 1 for the same number of frames, 5 frames, let's say. And then switch to object 2 for 5 frames, and then switch to object 3 for 5 frames, and so on. And we just keep going, okay? So we can do that by simply using rounding, but then also we need to use some invert, which we've already learned about, and some multiplication. Okay, so really simple. We have our frame number, so let's call frame number F. Okay, so as we move our frame number, that number, whatever is there, is F. And then X is our step size. In this case here on the left, these are a step size of 1. But here we want to be able to define the step size and say, well, maybe I want it to hold for 5 frames before changing. Okay. So what we do is we take the step size that we want, but we need to get the inverse amount of that step size and then multiply that by F. Because ultimately what we're trying to do is take our frame number and make it fit within this single step size. Okay, so let's say I wanted to have my step size be 5 frames. Well, what I do is I then scale my frames down so that 5 frames fit into within 1 unit. Okay, so each frame would then need to be what size? Well, 0.2 if I want 5 of them in 1 unit. So in other words, I need to multiply by 0.2 so that there are 5 frames in this 1 unit, another 5 frames in the next one, another 5 frames in the next. Okay, and then because there are 5 frames in each, my stepping will then be held for 5 frames, and then jumps up and then holds for 5, and then jumps up and holds for 5. Okay, so because I want a step size of 5, I need to multiply by the inverse amount, 0.2. It wouldn't help if I multiplied my frame size by 5, because then I'd be fitting every 5 of these steps would be in 1 frame. Okay, and that's the opposite of what I want. So we need to invert it. Okay, so this is the function that we're looking for. So after multiplying it, okay, so our frame number multiplied by 0.2 in this case, or in this here. So let's say we do it to 4. So we want a step size of 4. Then our invert amount, so our inverted X is 0.25. So there will then be 4 frames within this 1 block. So After doing that, though, the frame number is just a float. Okay, so let's say I was on frame 3. That would be 3 times 0.25, so that would be 0.75. Okay, 0.75 is not a step. It's still on the linear line here. It would still be on the gray line. So we need to remember that after doing the multiplication, we then want to round the number. And the reason I've got all 3 here is because we can do whichever one we want. It's up to you whether you want your rounding to go up or down or zigzag around the center line. Okay, so in this example, I've picked floor. So I've decided I'm going to go down. So I'm going to do this, right? So our x is 4. I want a step size of 4. So I invert it to 0.25. And then when our f is 0, we say 0 times 0.25. And then we floor it. So we round it down. Okay. So now here, 1 times 0.25 is 0.25. But if we round it down to the floor, then it's 0. And then we keep doing that same sum, and look at what happens. We get 0, 0, 0, 0, then 1, 1, 1, 1, then 2, 2, and it would continue, right? So 2, 2, 2, 2, 3, 3, 3, 3. So with this simple mathematical formula, we're essentially saying, I'm going to take something that is linearly increasing, like frame number, and I'm going to make it follow sort of steps. So I'm going to release the same number for 4 frames. And we can simply just change this x here to be equal to 10, and then it would literally hold 0 for 10 frames before holding 1 for 10 frames, and then 2 for 10 frames. Okay. And this can then be extremely useful in terms of like simulations. We want to maybe just suddenly step up the, a certain number, like maybe the heat of our pyrosim or whatever. And maybe we want it to increase in bursts instead of being linear. Okay. So we can get some sort of pulsing. We can get all sorts happening with this. And this sort of stepping versus here our looping are 2 of the most important features that you sort of will use in simulations. And then also here, don't forget our absolute and reverse, and negate, to sort of manipulate curves, whether it's curves that we're feeding in, so maybe ramps that we have control over, or noise functions that are giving you random kind of ramped values. You can make them all positive, or you can reverse them completely, or you could even do both and make them positive and then reverse them, and so you get only negative values. Great. So I hope you find that really useful, because these are some of the things I've used the most when working with simulations.